This video is going to talk through the CYK algorithm, standing for Cock-Younger-Kasami, for parsing a sentence. This will answer two questions: what sentences are grammatical, and what derivations correspond to those grammatical sentences. This will also let us figure out what is the most probable parse of a sentence. So without further ado, let's take a look at the CYK algorithm, where the C, Y, and K stand for Cock, Younger, and Kasami. Like we've seen before, we're going to use dynamic programming to solve this problem by breaking it down into smaller problems that we can easily solve. We will put the individual problems into a chart, and that's why this is sometimes called chart parsing. Each cell is going to encode some subspan of the sentence, starting at S and going to T. And we're going to ask, is there a way that non-terminal in can cover that span? Eventually, we want to take a look at the cell C0LS. Is there a way to cover our whole sentence with the start symbol? But instead of going top down, we're going to go bottom up. Here's the algorithm. You're given as input a binary grammar and no recursive rules. This means that you can't have the same non-terminal on both the left and right-hand side of a rule. You begin by initializing an array, and you set all of the entries to false. Unless you have evidence otherwise, you can't cover a span with a non-terminal. As with most dynamic programming, you need to have a base case. The base case for parsing is the singleton span. For each individual word in our yield, is there a production that produces that word? In other words, do we have a non-terminal that goes to this terminal? Now that we have spans of length 1, we need to see if we can cover longer spans. These spans start at position S and have length L. But to fill up a longer span, we're going to have to put two other non-terminals together. In other words, somewhere between S and L, we're going to have one non-terminal and then another. Let's call the change from one non-terminal to another the pivot position, and represent that with the letter K. Given all that, what we're trying to do is check whether there is some production rule that covers this possible combination of non-terminals that has a left-hand side alpha and produces a right-hand side beta and gamma. And with that, we fill up the chart position with two shorter spans. Remember, dynamic programming. So we check to see if we've already figured out that there is a span associated with beta and gamma that goes from the case of non-terminal beta from position S to S plus K minus 1, and for non-terminal gamma from S plus K to S plus L. If both of them are there in our chart as grammatical spans that were covered before because they're shorter, then we say, yes, we can have this longer span covered by non-terminal alpha. This is a lot clearer with an example. Our yield is book the flight through Houston, and there are some indices for the spans that we'll be using. For example, the token book starts at 0 and ends at 1. It's a span of length 1. This is our base case. So we first look at individual words that have a span length of 1 and find all of the non-terminals that can be associated with those tokens. Before we have the matrix C1 to determiner. So if this is true, then we write the non-terminal in the cell here. And if a word is ambiguous, like book, then we'll put multiple non-terminals in the cell. And in some cases, we can turn one non-terminal into another. We also need to consider that. Book can be a noun phrase all by itself. A verb can be a verb phrase all by itself, and a verb phrase all by itself can be its own darn sentence. So in this case, the whole sentence is book, like an imperative phrase. And then other words can be a noun phrase by itself. Houston can also be a noun phrase by itself. Now we need to start looking at longer spans and put together shorter spans into those longer spans. So first we look at spans of length 2 that combine two smaller spans of length 1. We can get a determiner and a prepositional phrase to combine together into a longer determiner phrase. So now we've gone through all the spans of length 2. We look at longer spans. This gets a little more complicated as we need to consider the pivot. You can put together either a span of length 1 followed by a span of length 2, or a span of length 2 followed by a span of length 1. For example, we have a span of length 1 that puts together the noun flight, span of length 1, and the prepositional phrase through Houston, span of length 2. This required us to have a pivot at position 3. The noun went from 2 to 3, and the prepositional phrase went from 3 to 5. So 3 was the pivot. the dividing line between the two subspans. We also need to consider other pivots. So for example, you might have had some combination of flight through as one subspan and Houston as its own singleton subspan, but there was nothing that was grammatical that could put those two things together. There's also a subspan of length 3 that combines a verb phrase and a determiner phrase into a sentence. This is obviously a dead end, as we want the parse of our entire sentence to cover the yield with a sentence, but we still mark it because it's part of our productions. At the very end, we're considering a subspan that's the entire length of the sentence, and there's only one derivation that explains the entire yield as a sentence, which considers book as a verb. So it resolved that ambiguity. So now we've determined that we should not consider book a noun in that context. So by this point, it should be fairly clear that the complexity of this algorithm is proportional to both the size of the grammar, that is the number of possible productions that you have, and to fill any of the cells requires you to loop over the length of the sentence again. But you also need to do that for each of your non-terminals, i.e. the size of your grammar. So overall, the complexity is cubic in the length of the sentence, linear in the size of the grammar. But there's nothing about probabilities here, and last time I gave you a whole spiel about how probabilities are super important for deciding between ambiguity in sentences. So what gives? We do indeed want more than simply saying whether a sentence is grammatical or not. We also want to be able to say which interpretation, which ambiguous parse you should prefer over others. And so this requires a tweak of the algorithm. Instead of just storing a Boolean variable, you should keep track of the maximum probability of the subspan that can go together to fill the cell. This should remind you of the Viterbi algorithm. This also means you have to initialize a chart so that the uninitialized spans have a 0 probability, and then you parse the sentence as before, look at the entry associated with the start symbol at the top of the chart, and that gives you the parse tree with the highest overall probability given the yield. Like before, we need to have back pointers so that you can recover the actual parse of the sentence. So this is the end of our mini-series on constituency parsing. To recap, we talked about a hierarchical syntax model called a context-free grammar. We extended that with a probabilistic interpretation so that you could learn to solve the problem of ambiguity. And now you have all the tools you need to teach a computer how to tell whether a sentence is grammatical or not. But this isn't the only way that you can do parsing. The other big option is to do dependency parsing instead of constituency parsing. So this is the end of our mini-series on constituency parsing. To recap, we talked about a hierarchical syntax model called a context-free grammar. We extended that with a probabilistic interpretation so that you could take a large corpus of parses, estimate parameters from that, and then solve the problem of detecting whether a sentence is grammatical and which interpretation, if it's ambiguous, you should prefer. So now you have all the tools you need to help a computer figure out whether a sentence is grammatical or not. But this isn't the only way that you can do parsing. There are other major alternatives, the most prominent of which is dependency parsing. If you want to find out more about that, check out the links in the description. This is just one video from a course that I'm teaching. If you want to get the whole context, check out the course webpage, linked below. There you can find all of the videos in the right order. YouTube likes to show you older videos out of order, homeworks, exercises, and recommended readings. And if you want to help other people find videos like this, please be sure to like and subscribe to provide a big gradient to the algorithm.